Welcome back to part two of coordination chemistry. So, last week we looked at a number of coordination complexes. And this week we're going to talk more about what's happening underneath. What's the theory? What's happening at a molecular level under these coordination complexes that explain, help us understand why or how the coordination complex is formed, is stabilized, and then also that gives us some insight into like the colors that we see from these complexes, right? The spectroscopic properties, the magnetic moments. So we're going to get deep down into some theory. So crystal field theory, this model describes the electrostatic interactions between the ligand and the metal's electrons. And from this model, we can gain more understanding about the structure, stability, color, and magnetic properties of coordination complexes. So, this theory focuses on the non-bonding electrons of that central metal atom, or the unhybridized electrons. So, whereas in Chem 400, the valence bond theory that explains how molecules are formed within the main group elements, right? Where we have this either sharing of electrons or this transfer of electrons. With crystal field theory, because we have a donation of electrons, we are focusing on the non-bonding electrons of the central metal atom. So we're not looking at metal ligand bonds, we're just looking at non-bonding electrons. And because electrons are negative, so in this coordination complex, the Lewis acid, right, receives electrons from our Lewis base. So in this case, with coordination complexes, our Lewis base are these ligands that we talked about. And then our Lewis acid is the central metal. So electrons are negative. So we have some electron repulsion that's happening between this Lewis base and Lewis acid, or the ligand and the central metal ion. So our non-bonding electrons of the central metal atom are in these d orbitals. We have 5 d orbitals. So each of these lobes here are the d lobes, the d orbitals within the metal atom. And each of the axes is the axes at which the ligand comes in and binds the metal atom. So in this first d orbital, each of the axes are labeled. But even though we don't see L, L is for ligand, the ligand is binding along each of these axes. So this is the splitting for an octahedral complex, right? Because remember, an octahedral complex has 6 ligands. 2 ligands bind along the z-axis, the y-axis, and then the x-axis. So we can see how the orbitals are like spatially arranged relative to the direction at which the ligand is coming in and binding. So in this first orbital, the ligands are directly like coming in a direction that's directly towards the d orbitals, right, along these y and x axes. In this orbital, the ligands are directly pointing towards the d orbitals along the z-axis. And then when we look at these three orbitals, the lobes are pointing like between the ligands. So there is less electron repulsion, essentially. So for an octahedral complex, when we say splitting, we're talking about how these d orbitals will split energetically. So these two orbitals where the ligand is pointing directly towards the d orbitals, right? That directness essentially leads to increased electron repulsion between the metal and the ligands. These other three orbitals, where the lobes are pointing between the ligands, those are lower energy orbitals because there's less electron repulsion compared to these Eg orbitals. So this naming for these two differences, energetic differences in the d orbitals, is based on or specifically for octahedral complexes. So here is like an energy diagram for how these d orbitals split. So this is what's called crystal field splitting. So notice those two orbitals that where the ligand's pointing directly towards the metal's d lobes are higher in energy. And this difference between where these two groups of orbitals are is called crystal field splitting. Crystal field splitting. And it's the sub OCT is short for octahedral. So this is the crystal field splitting for octahedral complexes. So the magnitude or the value of this crystal field splitting will depend on a couple factors or few factors, right? It depends on the charge on the metal atom, which d orbitals it occupies, the electrons occupy, and then it also depends on the nature of the 6 ligands surrounding the metal. So when we compare, if we're looking at, let's say, the same metal atom or same metal ion, we can compare the crystal field splitting that same metal is bound to different ligands. And this is called the spectrochemical series. And this is just a summary of some of them here, right? Where these atoms or these ligands are ranked based on what's called their field strength. Their field strength. So iodide has the lowest in this series, right? Whereas cyanide has the highest. So that means that if we take, let's say we have iron 2+, if it's, and we compare it to iodide and cyanide, the magnitude of this crystal field splitting will be much less for iodide than it will be for cyanide. And we're going to talk more about what that results in terms of how the electrons feel in these orbitals as a result of that. So I'm going to pause here and pick up here in the next video.